So while talking about the summary of the activities that we need to do with different timelines, this slide gives us an overview where we need to do a functional baseline at the end of the concept design, where the system requirement spec is baseline, and those are the requirements that any contractor who's delivering a design and a construct project will need to adhere to them and provide compliance and conformance evidence against them. If you look closely or read, there is a key aspect here that you can see that there's always a disintegration, further step down. So at a concept design, you have got a high level system, but then at a preliminary design, you know more, you dig deep, you get a subsystem level, and then you can go to a component level. So this is basically talking about a product. So the more you design, the more information you have, the more you dig deep, the more change or more derived requirements you will get. When I use the term derived requirements, those derived requirements are basically coming from the functional baseline of a system requirement. A system requirement can be to deliver a rolling stock with XYZ speed, but in order to do that, let's say a rolling stock that can operate at 160 kilometers per hour. But then the requirements that it will have that will be further drilled down is how a rolling stock will do it. The designers who are doing the preliminary design or a detailed design will need to come up with the things that they can do, the design that they can implement in order to come up with a rolling stock that can meet that criteria. And that criteria is really important. So those requirements that they come up with are basically the derived requirements that make up the functional baseline. So we'll touch on how requirements are structured at a later time. So preliminary design, we've got the allocated baseline, and then at the detailed design or IFC, we have got a product baseline where we know the design is finished, we know how a product will look like, and then the construction starts, or commissioning starts, or manufacturing starts, and then we get to see the physical layout, the physical element, or the physical subsystems or system that we designed in our PD and DD and IFC stages. So the left-hand side again is the side left-hand side of the V life cycle, and the right-hand side after construction is basically the right-hand side of the V life cycle again. And during all this process, you do audits. Like in the right-hand side, you can see at the bottom triangles that the FCA, functional configuration audit, or physical configuration audits, or test readiness review. These are all that span between the timelines. You might be doing an FCA at the end of a design and then doing a PCA once something is commissioned or constructed. And then you might be doing test readiness once you have integrated everything, or you might be doing test readiness prior to integration, and then once integration is done, you are doing an integration readiness review. So it's a bit of a chop and chain, but the key idea is that you do run audits. The audits are there to verify and validate that the compliance documentation that you have provided meet the intent, meet the criteria, are providing enough conformance evidence, and etc. So that's pretty much the summary on systems engineering. In a nutshell, that's how system engineering works. We'll move on to requirements management, which is the key part where you would have heard me in the past half an hour talking about requirements, system requirements, system baselines, and whatnot. So now we'll focus on requirements management and how we come up with these different level of requirements at different stages of the V life cycle, and how we provide verification and validation evidence against them. Trying to define requirements is quite simple. Requirements are the defined aspects that design needs to meet, or a construction element needs to meet in order to construct a system. Then the requirements management is basically a set of activities that help out that process of identifying elicitation of requirement, that helps in documenting those requirements. Requirements management is a way of refining those requirements, tracking the changes that can happen during the life cycle. Like I said, that it's an iterative process. It can change at any time because of the information that you have got. But all of this needs to happen in a fashion that it records. You have got records of every change. You have got records of all the documentation that has been produced. You've got record of all the argument that you have made during the process of coming up with the requirements. In order to document how our requirements will be managed, there's in project there's always an RMP, a requirements management plan. Sometimes it's part of a system engineering management plan, SEMP, and sometimes it's not part of that, depending on the project or needs of the client. Clients might say that we need a separate RMP document because such a big complex project, or they might be comfortable with merging it with other documents. But what it does is it maps out a strategy, it maps out a plan where you need to meet those criteria, where you need to meet those aspects, processes, tools, utilize those tools, and perform requirements management throughout the life cycle. There are several tools available in the market. One of the key ones that is used in Australia is DOORS. It has got two versions. One is classical and one is NG, which is next gen. NG is over the internet. It's a cloud-based, but classical is basically server-based, where you install a server, install it on a basic hardware computer, and then you have to provide updates to that software and work in tandem. So those are the two versions of DOORS that are available in the market, and industry has adopted to them quite diligently and is utilizing it in all the projects across Australia. There's another one that's from memory, Comply Pro, if I'm not wrong, but it's not been widely used, although it provides the same functionality. But those, I think, stepped into the market at the right time, so maybe that's why. Moving on to why we do requirements management now. There are several aspects to it. It provides us the means to basically clarify to the client that we have delivered on our promise. It provides traceability on how we delivered to our promise. It provides, most of all, it provides a single source of truth. It's very important to have a single document or single source where you can go to at any time of the V life cycle of a project, and you can identify that what you need to do in order to meet the final outcome of the final system. So that single source of truth will contain who changed what. So those softwares that I mentioned are being used because they keep records of who made the change, why they made the change. It records description, it records baselines, it records version details, it records historical evidences in documents. You can upload documents into those databases as well. So those are the sort of functionality. Like I said, single source of truth is very important to manage a project, because 10 years down the line, somebody might need to reflect upon a decision that was made 10 years back during the design life cycle, and somebody made a change, a small change that needs to be documented. And that's how you document stuff in those. And obviously traceability to derived requirements, how derived requirements collectively meet the intent of a high-level requirement, and vice versa. Benefits. Requirements management has got loads of benefits. If we look at the key one, is basically to reduce cost. So imagine a world where there's no tracking of what are the requirements, what you need to deliver on. Imagine a world where you change something without informing someone, without recording it, or without it being widely known in your isolated office box, and then you realize that the change that you have made has had a repercussion. So it's basically reducing that cost element, that if you work in your silos and you don't deliver on what is intended and what is widely known to everyone, like if someone is designing a rolling stock, imagine you know that you are building a 8-carriage rolling stock, and somebody says, no, I'll build a 7-carriage, and they'll design it 7-carriage, but a widely known figure was 8, and everyone was designing to 8. So those are the sort of things that might have an impact. So the thing the example I used obviously won't happen, but these kind of things can happen at a minuscale, at small design details. So it's really important to record these changes, record these updates, and make them widely known so that everyone is designing to the same single source of truth. It improves the quality of the outcome, obviously. It decreases the time taken. It decreases the rework that might happen because of mistakes or not recording changes. It de-risks as well. De-risk, like I said, meaning that the aspects that are not being designed as part of the whole team and working in your silo, or making a change that is not recorded and is not known, then it might create a knock-on effect of an incident happening later in the piece. So it provides that exercise of managing risks. It provides that exercise of recording them and documenting them, and closing them off with appropriate evidence, with appropriate recording of why some steps were taken and when they were taken. Effective scope management, it helps to gauge what you need to deliver. It helps you keep the scope clear, and that's how your projects or the contractors can basically put a cost upon stuff, because they know the requirements that they need to deliver on. If they didn't know what the requirements of the client were, then they won't be able to gauge what they need to deliver, what product they need to deliver, what railway system they need to deliver. So that's one of the key things that helps in scoping, that helps in identifying what needs to be done in order to deliver a railway system. And then somebody can gauge, somebody can put a cost price onto it, and then that's how project bids work. And then obviously design documentation reports and all of the stuff is documented and recorded, and you have a relationship with requirements of everything that is happening around on the project. Moving to requirement solicitation. So this is the process that happens behind the scenes. So this is a process not everyone gets involved in mostly, because this requirement solicitation is a process where the business needs are converted into stakeholder needs, which are converted into system requirements. And this is all iterative. This is all based on the design information that you have got at that point in time. And then you go back and forth. Business need can change based on the information provided, or stakeholder need can be toned down or toned up. It can change in a year's time while people are working on a project. And that is the reason why the projects that start, or the life cycle of the projects, if for a railway system it is 5-6 years of a mega multi-billion project, the first year or so is basically spent on coming up with these requirements. So you will see behind the scenes announcements that works are happening, but the things that are happening are basically coming up with requirements, identifying the business needs, identifying the stakeholder needs. When I say stakeholders are anyone impacted by a change or a new asset. So a stakeholder will be me as a customer on a railway system. I'll be impacted by a new railway station next to me. How I sit, how I behave in a rolling stock, how station interacts with me, how I enter a station, how I exit a station. So I become a stakeholder as a customer. Someone who is an O&M, an operator and maintainer, is a stakeholder. Client is a stakeholder. So it's basically identifying the stakeholder needs that dictate the course of action, and that drop down into system elements or system requirements, which are then once system requirements are identified, then they are sometimes drilled down into your contracts. Contracts will have much more information than a system requirements, and sometimes contracts lead the system requirement, form the system requirements, and then you drive your subset of system requirement based on those contracts. But you need to always do a system requirement specification, an SRS baseline, because without it, you won't be able to track the changes made after that. So like I said in a couple of slides before, that there has to be a line drawn in sand where you have got a functional baseline, a baseline of system requirement specifications, SRS, where you know what you're designing to. And then you can change the derived requirements that are linking up to those SRS. So this is an iterative process. It goes back and forth until business needs is finalized, until stakeholder needs are finalized, and finally your system requirements are finalized. If you look at the relationship between requirements analysis, look at the functional analysis, and then design synthesis, like I said, it's an iterative process. There's a 3-step process which goes back and forth a lot. When you look at functional analysis doesn't mean that it's not going back or not going to change the requirements. It can impact. There are projects that work on functional aspects later because they know what they need as a system, but then you need to consider the functional scenarios. In a railway, the operating mode scenarios impact the functional scenarios, like you have got emergency modes, you've got degraded modes, you've got normal operation modes, emergency modes. So those modes impact how a system will function, how a tunnel ventilation system will function, how it will update itself, how it will operate itself, or an operator will need to intervene in XYZ. So it's an iterative process of identifying functional scenarios and functional elements, and then allocating them into the, if you look at the design synthesis, design elements. So A design synthesis is basically development of a design from concept to preliminary to detail to IFC document. So a design that goes through that life cycle stages where you have got no information and you are building a concept on a piece of paper. You are identifying uh, what your design will look like, and then suddenly you realize that okay, like for concept you might know that you'll need to build a bridge. Your first concept is to build with 2 support system, and then you go on and you realize that you did surveys, it will need more support, it will need that kind of a structure, it will need retaining walls and whatnot. So you go ahead, and the more information, the more design you do, the more surveys, the more information you get, the more chances there are that you will impact the initial requirements. And you might change your derived requirements. You might change the way you were looking at things 6 months ago because you didn't have that information. In projects where there are interfaces, when I say interfaces, basically you're having 2 different projects coming together and making one system. So 2 subsystems making a big system of system. So when you look at that aspect, you'll have different aspects they are working on, and when they combine them, then there will be some unknowns. And when you know, get to know the information that the other team has got, for example, tunnel ventilation, rolling stock operation systems, one organization or one entity is designing a rolling stock, the other is designing a signaling system. When they need to talk to each other, there has to be information exchange. So the interface point is how they will communicate. So one rolling stock might start early, or the signaling system might start working early, and they won't have the information that rolling stock would have had, or rolling stock might be late to the party. So those are kind of things that evolve. It's an iterative process. Like I said, it's being updated requirements, not the SRS, derived requirements that keep updating, that keep changing and chopping. And later on, we'll see how we record those things. This is another portrayal of how these things work. How they interact with each other, requirements analysis and their verification, functional analysis and their verification, and similarly, the design synthesis or design verification is the last step before getting things to construction. I'll keep it short, but this is a diagram from IEEE 1220 standard as well. This depicts that when you're going through a requirements analysis and illustration process, what you need to consider. You need to consider interfaces, system boundaries. You need to define operational scenarios which you will be designing to. You'll need to inform what are your performance requirements, what are your functional requirements, your different modes of operation, like I suggested. So these are the key high-level elements or items that somebody needs to consider while doing the system requirement specification or design analysis. Even if you look at the design, a design will need to know what are its interfaces. It will need to know what are its human factor issues. It will need to know what are its performance requirements. Our rolling stock design will need to know what am I designing to. I know I need to design a rolling stock, but I need to know the performance. If I'm designing a substation, I need to know what kind of power at what load and whatnot. If I'm designing a control system, I need to know how many IOs it has to support, what power it needs to support, what array of logical inputs and outputs it needs to support, what kind of redundancy it requires. So those are the kind of things, while defining your requirements, you will need to know. Otherwise, you won't be able to deliver the right system that meets the needs. And like I said, it's about designing, informing, and then coming up when you do the final baseline where you realize that, okay, we did our preliminary design, we had system requirements, we did our preliminary design, and now we know what we are designing, because this is the point where we have enough information to go forward and do design and construct. And that's where you draw a physical product baseline, and a baseline where you can look towards and verify and validate. We talked about system breakdown structure, how system was disintegrated into smaller subsystems. And in a similar fashion, the requirements is also broken down in a requirements breakdown structure, where there are a high-level requirement that gets smaller pieces and it goes to a smaller and a smaller scale. Now, the way it has to be that the requirements, if you look at this, requirement 1.1.1 and 1.1.2 collectively should satisfy. And the condition is that they should be collectively satisfying the high level requirement. If they don't, then it means that either they are not defined correctly, or they are not defined in the same, they are not defined in the right requirement. So that's the key. So when you're defining requirements, you have to allocate them or put them in a hierarchy. If you don't put them in the right category, if you don't put them into the right high-level requirement, you won't be able to satisfy the high-level requirements. And if you're not able to satisfy, when I use the term satisfy, it's about verification and validation. So if you're not able to satisfy the requirements, you're not able to satisfy the system, and then you won't be able to build properly. I'm not saying that you won't be able to build, but it will have loopholes that you'll need to then identify that where did that requirement go. I might raise a requirement that I thought sat in the requirement 1.1, but it might be the case that it was flagged wrongly by someone else and sitting under some other umbrella of requirements. And hence we lost track of the importance of that requirement and the contribution it was making to the 1.1 set. So it's very important that whenever you're classifying requirements, it belongs to the right high-level requirement. Talking about requirements hierarchically, then once we have identified all the requirements, I'll skip this and I'll move to this one. So once you have got the requirements breakdown structure, where you have got all the requirements identified with the allocation hierarchical numbers, then what you have got is on the right-hand side, you have got a physical allocation, a physical system, and your each requirement is attached or linked or allocated to that physical system. I've seen that done with on projects where a design package or a design element was used as a physical allocation. I've seen that the work breakdown structure elements were being used. So it depends again on the ease with which you can deliver, with you can justify, with which you can integrate and test a system. If your integration and testing requires you to make it a product based, it requires you to make it an element based on my experience, then you allocate it to that. So there is again not written in stone what you allocate it to, it's what you can allocate and verify to. So if you can verify it on a system, then you should allocate it to a system. If you can verify and validate it to a design package number, then you can do that as well. Depends what you're allocating it to and how you're verifying and validating. So like I said, requirements management plan documents that at an early stage, how you want to see that happening. On projects that I've worked on, I've seen it on design packages because mostly the whole railway network is disintegrated into smaller work packages, smaller contractual obligations, and hence you can measure them, and then in tandem you can basically meeting those criteria. By meeting those criteria, you can meet the bigger intent. That's how I've seen it implemented. I haven't been involved in any specific product manufacturing, so I don't have that kind of understanding of the application on a product, but I understand that it will be based on elements, the elements of physical entities or physical units or smallest possible unit within a equipment or a product where it will be allocated to, because each requirement will have to have a different home where it will be satisfied. This example is from aerospace. So it shows us that if 1.1.4 is there, it will be attached to a fuel, or sorry, allocated to a fuel. You have got wings and fuel usage. You've got requirements. So they have linked it to the physical items that they will produce at the end of the day. And then once they go about verifying and validating these requirements, they will see that their wings and fuselage is basically up to the design requirements or the requirements that were set out at an early stage. So it depends on how you envisage your integration and testing that you can do that. So this aerospace one is basically utilizing physical items on an aircraft and allocating requirements onto those physical items, and then they can integrate them with each other easily. The two last things that are key elements of requirements management is requirements verification and requirements validation. Requirements verification is basically confirming that what we promised in our requirements spec to deliver, have we delivered based on that. The common aspects or the common items or documents that provide that verification evidence are basically your design documentation, your survey documentation, your simulation tests. This is a extract from ASA standard, which talks about how requirements are verified. It gives us a brief overview of what's expected when you go about verifying a requirement. So There are a couple of key items here. I won't go through everything, but what I'll do is I'll touch upon the key elements. That the key element is, one of the key elements is identifier. You have to have a unique identifier for each requirement. If you don't have that, then you will lose the authenticity, the uniqueness of that requirement, and then you lose the whole history that we were saying earlier that is very important to keep track of the changes, to keep track of the modifications, to keep track of any updates that are being made by anyone on the project. So unique identifier is really, really important. Then next one is basically the method, that how you are providing the verification. Are you doing an analysis? Are you doing a simulation? Are you doing an inspection or a review of a document? Are you doing a physical inspection? So those are the kind of methodologies that ASA and other organizations require you to identify at an early stage. When you identify a requirement, you identify what methodology you will use to demonstrate that it is verified. The other one is status, important, that you need to show that if it has been reviewed or it has been canceled, deleted, what happened, or is it no longer applicable and whatnot. Then there has to be what kind of test they are looking at, what kind of results they are looking at, if it is passed or not. And those are the kind of elements they are requiring. Who executed the test, what date, what was the outcome, and what was the passing criteria. So these are the few things that make up the whole verification evidence, or the verification detail, where it provides confidence to the reviewer, it provides confidence to the client that the things that our project needed to deliver, the verification they needed to do, they have performed it. Moving on to validation. Validation is basically confirmation that what we have built meets the needs. So in a nutshell, verification is, have you built the system based on a design? But validation is if the system built meets the needs of the customer or the needs of the business that we were identifying at an earlier stage. So those are the two distinguishing factors. Looking closely, verification is done mostly on design or at par on physical tests. But then as soon as you go into the world of a final product, when you go to integration testing, when you go into a world of physical product being handed over, that's the validation phase where you say that I have created this product and this is the final outcome. Air shuttle, it might be that each equipment on its own had its own validation, its own verification, but as a system of a whole space shuttle, they must have a separate validation activity that involved integration and testing. So verification validation cannot be used interchangeably, but can be based on a system or a subsystem or a system of systems. Typical validation evidences are something similar to verification, where you have got a unique identifier which is being used in a similar fashion. Who executed the validation test? Does it involve your FAT, SAT, SIT? Was the result satisfactory? What was the success criteria? So both are similar in fashion, but the detail level is different. In the verification, you mostly have design documentation or surveys, and in validation, in our field, in railway industry, and in validation, you'll have mostly physical FAT, SAT, and control systems, physical as-builds, physical red line markups. You'll have in inspection and test reports, you have got physical structural certifications, structural proof testings, and whatnot as your physical evidence of constructing to the requirement. Again, the kind of validation evidence and the verification evidence varies from industry to industry, varies from the requirement to requirement. The last thing is configuration management. I just included it as a side note so that anyone who is interested can go into the details of config management. Config management is a system, part of a system engineering process, which keeps track of what changes that are being made, that are being brought about in a system, that are being brought about during the design life cycle, and how you track them, how you modify them, how your subsystem will interact with each other, what are the interdependencies. So it's basically keeping track of all those things. Configuration management identifies your configuration items, which are basically anything that you want. You can identify documents as your CIs. You can identify your physical items like in a shuttle, again, a fuel system or wings or XYZ as your CIs. You can, in a rolling stock, you can identify the carriages, the brakes, the wheels, the vents, as your CI. So it depends on how you are managing your interfaces, how you are managing your system, that you can go to the smaller CI. Then you can go to, at utmost level, again, it's not written in stone what is classified as a CI. It's dependent on the project. It's dependent on the approach of the client. Client might have different requirements in their asset management system. They might have different classification of CIs. They might have different definition of CIs, different level of CIs. So you might need to map to those. So it depends. Again, it's not written in stone. I haven't seen it written in stone. I've seen it used interchangeably in different projects, and hence that's my understanding as well. Lastly, why system engineering is important. The curve that you can see on your screen is basically highlighting that on the y-axis you have got the cost, and on the x-axis you have got the life cycle. The upfront cost of system engineering, identifying the right requirements, flagging them in a right manner, documenting them in a right fashion, clearly articulating them, making them tangible, making them trackable, traceable, making them quantifiable is important, and that takes time and energy and some informative design. If you do that upfront, that is a good cost. I'm not saying multi-billion dollars, but it is a big chunk of money. But as soon as you go down the road of developing your systems, designing your system, constructing your system, the cost wears off because it's now tracking time. If you have done the hard work earlier, the later on you're just doing traceability, you're just modifying small stuff, you're doing just iterative changes, you're not developing the system requirements, you're not developing business needs. But early on, that's a cost. I don't have the other graph, but the other graph that I wanted to include, I couldn't find it, was that it showed that if you do, and I think I don't have that, if you make changes, these changes in requirements, if they are not, if the money is not spent at an early stage, the impact will be that you are going to spend that money during detailed design. You're going to spend that money when you find out that the design that was constructed was not conforming to anything, or the requirements were not prepared correctly, or were prepared in a hurry and were not concise, were not clear, and were not informing. And hence the designer thought it was XYZ, and they designed it in a different fashion, not meeting the intent. And you realize that now you have to go back and redesign it because the design doesn't meet the intent, because it's not a clear requirement. It's not providing you precise information that what you need to deliver. And hence the basic notion, or the basic thing that system engineers want to portray and inform people is that the upfront cost is more, but you can save millions of dollars later on because you won't be needing to do rework. That's pretty much it from my end. Happy to field any questions on the